In this video, I will focus on discussing the bound volume and surface currents in relationship with the magnetic vector potential. Now, to find the magnetic vector potential as a function of the observation location, okay, when I say R_obs, this is where you want to find your magnetic vector potential. One way to do the calculation is by using this volume integral and the closed surface integral. Now, the volume integral, other than the constant, is the volume integral of a volume current density, JB, the bound current density, and this is of course a function of the source position. Okay, these volume currents, these are the source, the ones that create the magnetic vector potential. That's why this is a function of our source, and over R, where R is, as usual, R_obs minus R source, and this is differentiating over integrating over dV, an infinitely small volume. And then we add to that the contribution of the closed surface integral of the constant, and that will be the bound current density, or this is a surface current density since this integral is over a surface, over divided by R times dA. Now, by definition, okay, what we have here, the volume current density and the surface current density. To calculate these two current densities, we need to know the magnetization of the material, and this M refers to the magnetic dipole moment per unit volume. And if we know this, we can take the curl of it to find the volume current density, and if you do the cross product of the magnetization with n hat. Now I want to talk about a little bit briefly about this n hat and what it is. It is of course a unit vector, and it points in the same direction as the vector, the small, infinitely small vector dA. Okay, those two are parallel. Now, I want to talk a little bit about the meaning of these two current density. Okay, so both of these, they are, at the end of the day, they are current densities. Okay, they refer to currents. Now, okay, if this is, okay, this is my material and it is magnetized. One way, as I mentioned in my previous video, in magnetism, when we talk about the magnetic fields in matter, we start thinking in terms of currents. You can model a magnet in terms of a current flowing in a circular loop of wire. Okay, they have the same distance dependence. So the way that we can think about a material that is magnetized, has some magnetization, is by thinking of it in terms of infinitely small currents that are flowing in it. Now, whether you do circular loops or square loops and so on, it doesn't really make a difference at the end of the day. It's the same conceptual, the same qualitative conclusion. Okay, and all of these that I'm drawing here, these are just currents flowing in the material. Now remember the case with electricity, we did have, in electricity, we do have electric monopoles. Those are what we call the charges. In magnetism, there are no magnetic monopoles. So the lowest term that you can start with, if you want, in your expansion is the magnetic dipole. So that's why I'm using magnetic dipoles. These currents flowing in circular loops this is each one of them corresponds to a single magnetic dipole. Now, if you make the assumption that all of these magnetic dipoles are the same, then if you look closely, let's say I'm gonna focus on this area over here. Okay, if you look closely, the current here is flowing downwards, whereas the current in this loop flows upwards. At the end of the day, these are so close that we can make the assumption that their magnetic effects, or whatever magnetic field they create, is going to cancel out, because you have two currents flowing in opposite directions and they are so close. If we think about this and all the magnetic dipoles are the same, then what is left are all the currents that we have on the surface, and those are not flowing in canceling directions. Those are all flowing in the counterclockwise direction, the way that I did these magnetic dipoles. This will give rise to your surface current density. Okay, so this will be your KB. Now, in the case where all of these magnetic dipoles are not identical, then inside, in the volume of this material, your dipoles will not be able to cancel out their magnetic effects, because even though the currents may be pointing in opposite directions, if one of them is a stronger dipole than the other one, then of course at the end of the day you will have a contribution to the magnetic field, or the vector potential if you want, due to that dipole. That's when your magnetization is not uniform, then this will give rise to your volume current density. Okay, this is inside the volume of the object. So this is a qualitative picture, a way to think about what happens when you have some magnetization in a material, and the way to calculate the magnetic vector potential. And I mentioned in the past, this is not really a very useful concept. I have not seen being used in practice really. But in any case, the way to calculate this quantity is by thinking in terms of the volume current density, the bound current density, and also the surface current density, which if you have the magnetization, you can find those two quantities.